Very good afternoon to all. It is our great pleasure to welcome you all again for the day 2, second session of 2 days international conference on international seminar on advances in materials and manufacturing. So now we have Dr.V.Balasubramanian sir, Professor and Director of Center for Material Joining Research, Annamalai University. Shortly, sir is called as Dr. V.B. So I believe that no one will be without knowing this short name. So it is my pleasure and it is our proud to have Dr. V.B. sir in this wonderful forum. Let me welcome you all to this forum, and I request Swapna to introduce SARS formally.
Good afternoon, everyone. Myself, Swapna Sai, pursuing second year mechanical engineering in Chennai Institute of Technology. Dr. V.Balasubramanian, professor in Department of Manufacturing Engineering and head and director in CMJ and RE at Annamalai University. He did his PhD in IIT Madras. He has about 27 years of experience in teaching as well as in research. His research interest involves materials joining and surface engineering. He is a life member at Indian Welding Society, Indian Institute of Welding. He has published about 400 research articles in national and international journals as well as in conferences. I welcome you, sir.
Can I start?
You can go ahead, sir, please.
Okay. Can you hear me now?
Yes, I am able to hear you, sir. Are you sharing your screen, sir?
Yeah, it's a screen.
Yeah, please, sir. So,
is it visible or?
No, not visible, sir. You can go for the third icon, like computer symbol, sir. You can go.
Okay. Yeah.
Sir, sir?
Yeah, 1 minute.
Okay, sir.
So I have to, this files, no? I will go into the file or?
No, sir, now first what you have done is correct. Then now you have cancelled your screen sharing, sir. So you should not click that again. Now, please turn on screen share. Then minimize your browser. Then open your PPT, sir.
You okay?
Not
No.
yet, sir. Not yet, sir.
Last time I did.
Yes, sir. Now you have done correct only, sir.
But to close this screen, huh?
Yes, sir. Sir,
Yeah.
as soon as the third turn screen share is on, one pop-up will come. Then you have to select the entire screen, then share.
Oh, entire screen. Okay.
Yes, yes.
No. So, turn screenshot. So your entire screen is coming, but it is not. I'm not able to click that.
Entire screen. Sir, entire screen, once if you click inside, the enable share will be enabled, sir.
So screen you have to click, right?
Yes, sir.
Yeah. Okay. Good.
Yes,
But
sir.
it is coming
Fine.
like this.
Yes, sir. Fine, sir. Now you minimize your internet browser, sir. Minimize your internet browser.
Okay.
Now please open the PPT, sir. Now it is coming good, sir. Please open the PPT. Yes, sir. Fine, sir.
Okay. Right.
Sir, please
Shall I stop?
please go out, sir. It is perfect, sir.
Okay. Thank you. Thank you. Good afternoon, friends. First of all, I wish to thank the organizers, Chennai Institute of Technology, for giving me an opportunity to share some of my experience on this topic. The two-day international seminar by online is organized, and the theme of the seminar is Advances in Materials and Manufacturing. And once again, I want to thank Dr. Dinagaran, the coordinator of this program, and also the principal, Dr. Parthiban, for inviting me to deliver this lecture. So today I just want to share my experiences with joining techniques for dissimilar non-ferrous alloys. So today I want to cover, I will try to cover based on the time limit available. Briefly, I will introduce the concept of dissimilar material joining. Then there are many methods available, many joining methods available. I want to focus on these 5 joining technologies today's lecture. So why we need to join dissimilar materials? So mainly the present day, whether it is a transport vehicle or aircraft vehicle or shipbuilding industries. So the main motto is we need to reduce the weight of the structure. So if you want to reduce the weight of the structure, in some part, in some portions, in some of the components, we need to replace the high density material with the low density material. So that's the one reason. Another reason is there are methods to improve the energy production, and also to create next generation. Even in the medical field, we need to create a lot of medical products and medical devices, and many other manufacturing industrial uses that requires joining of 2 different materials. Actually, dissimilar welding is there are 3 different classifications of dissimilar materials. Here it shows, you can understand, joining of different type of metal. So 2 type of metal. One is steel with nickel, and copper with aluminum, copper with stainless steel. If you see that, the melting point is different. Steel, the melting point is different, and nickel, the melting point is different. Similarly, copper and aluminum. Copper, the melting point is 1050 degrees centigrade. Aluminum, the melting point is 650 degrees centigrade. Similarly, copper with stainless steel. So this is entirely 2 different types of metals. And second classification or second group is, it is joining of different alloys of same base metal. So you have same group, steel with cast iron, stainless steel with carbon steel, These are all belongs to the same group, ferrous materials group. You know that in metallurgy you have metals and alloys, you have ferrous metals and non-ferrous metals. So these two comes under the ferrous metal category, steel with cast iron, stainless steel with carbon steel. And similarly, aluminium. In aluminium, you have 8 different types of grades, starting from 1000 series to 8000 series. So here, the 2 different grades of aluminum alloy, 5000 series with 6000 series. Similarly, you can join different grades of aluminum alloy. This is also one type of same group, let's say ferrous metal or non-ferrous metals. But within that, there is a different metal joining. That's called second group. And third group is joining same metal but using different alloying materials or the pillar metals. For example, if you want to join, so aluminum 6000 series. So both the side you have the aluminum alloys, which is 6061. But the filler metal normally used for joining these two aluminum alloy 6061 with 6061 is 4000 series filler alloy. That is 4043. So this filler is used to join this aluminum alloy because mainly to avoid the hot cracking problem. And similarly steel with nickel. So you can join steel with the nickel based welding wire. So steel and steel. For example, you can join the austenitic stainless steel with using the nickel based alloy. Armor steels, you can use the austenitic stainless steel filler. So the weld metal, the base metal is same. Both the side, the base metal is same, but the weld metal is different. The welding and the weld metal is a different weld metal. So this is also comes under the dissimilar materials category. So two different materials we are joining. Left side and right side you have two different materials. And here in this category you have same class of materials, but here same material, but the filler metal is different. So like that, there are lot of types of dissimilar welding will come into picture in the actual fabrication. So what are the problems? Why the dissimilar material is a big challenge? Because it's there is a difference in physical properties. Physical properties means it's a difference in melting point, difference in density, difference in thermal coefficient of expansion. So copper and aluminum, I told you, copper is 1050 degrees centigrade, aluminum is 650 degrees centigrade melting point. Similarly, density is concerned, density is more and the aluminum density is less. So difference in mechanical properties, strength is different, hardness is different, toughness is different, and difference in metallurgical properties. Sometimes crystal structure itself will differ. One material is BCC, other material is FCC. Suppose if you want to join aluminum with magnesium alloy, aluminum is FCC metal and magnesium alloy is SCP metal, and microstructure and chemical composition. So these are all challenges because if you want to join similar category of material, that itself a challenge. But when you want to join two different types of materials, then it is a big challenge for the welding engineers. So there are many combinations now used in the industry: aluminum with copper, aluminum with steel, stainless with copper, aluminum with titanium. So different combinations are worked out, and it's successfully welded also now. So these are some of the applications where you have this. If you take, it's a copper is the top and the bottom is the stainless steel. Here it is copper is the bottom, and here it is the aluminum alloy. So here it is the carbon steel and aluminum alloy. So here also it is the copper in the bottom, you have the carbon steel in the top. So these are different applications, lot of applications are there. So there are many methods available, many techniques are available, many technologies are used to join dissimilar material. For today's class, today's lecture, I want to cover some 4 different processes which we have facility in our center, and we also did a lot of work on these processes. I want to share some of the experiences of this. So first one is diffusion bonding process. So diffusion bonding is mainly caused by the diffusion of atoms. So atoms, movement of atoms from one location to other location. So this movement of atom will occur mainly because of there is a gradient, thermal energy gradient is there, then the atoms will move from one place to another location. So there are many examples are there, and if you see this too, I want to join copper with nickel. copper alloy with nickel alloy. So these red atoms are copper atoms and these blue atoms are nickel atoms. So this is at high temperature, but you require high temperature. When you heat high temperature, these red circles and the atoms will move towards the nickel side, and nickel atoms will move towards the copper atom. So there is a concentration difference will occur between them, and in between they will meet. Copper atoms and nickel atoms will meet, and they will form some intermetallics. They will form, and that is by that the bonding is occurring here. You can see here in this diagram, you can understand clearly. Copper atoms moves towards this direction, and nickel atoms moves towards this direction from nickel. From copper, it is moving here. So here, if you see that, in this case, copper and nickel, there is the atomic size, the atom size is almost similar. So they are replacing. If the nickel atom moves towards this side, there is a vacancy produced here. That vacancy is filled by the copper atom, which is moving in the opposite direction. And like that, the vacancies created by these atoms, movement of atoms, will be filled by the movement of atoms from other side. So after diffusion bonding, you can see from the center, from the top surface from the center, if you measure that, the copper gradient will vary, the concentration will vary, and nickel concentration also will vary as it's shown in this graph. And there is a law, actually it's proposed by Fick's law, popularly known as Fick's law. There are two laws. One is steady state diffusion, other one is non-steady state diffusion. So steady state diffusion is diffusion rate is not proportional, it's not a function of the distance and the time. But in the non-steady state, it's a function of distance and the time. That's called the Fick's second law. So this is, you can see this in this diffusion process is condition to occur, there must be an empty site. There should be an empty place, vacancy site. The atom in one location, the atom should be vacant. If there is a vacant, then the atoms, and also the second condition is the atom must have sufficient energy to break the bond, because between the atoms there is always bonding. Metallic bonding is there, ionic bonding is there. You heard about covalent bond, and there is a forces like the van der Waals forces. So that one atom want to move from its original location to another location. First, it has to break its bond from the neighboring atom. If it breaks the atom from the neighboring atom, then only it moves. So if you want to move to get that energy, then it requires the energy from the outside, external source of energy. So when you heat, then they get the energy. So because of that energy, the atoms will break from that bonding, and then it is free to move from its original location to other location. Even if it moves, there should be a vacancy, then only it will move. Otherwise, it cannot move here. So if you see here, there is a vacancy here. This is a white spot is the vacancy. So this atom will move from this pink color atom will move to this the white atom. That's a white space. That's a vacant space. In the next one, from the top. So once it becomes, this area will become vacant here. So this atom will move from top to here. And in the next case, so this will become vacant. So what will happen? This atom will move here. So like cyclically, there is a movement of atoms will occur. So this is the basic when you want to join two different materials, and the movement of atoms from one material to other material, the atoms will move. So to move that atom, you need some temperature. You need to heat the material. Then only the atoms will move by breaking the bonds between the atoms. So this is basically diffusion bonding is a solid state welding process. Why it is called solid state welding process? Because there is no melting at all here. In the solid state itself, well below the melting point of both the materials, the bonding will occur. Normally, welding means that people used to say there should be a heat, and that heat should melt the material. The material will be taken to the liquid state. In the liquid state, there will be coalescence or fusion will occur. But in the solid state welding process, there is no such phenomenon here. So the welding or bonding takes place well below the melting point. So the material will not be taken to the liquid state. In the solid state itself, this movement of atoms are happening. Because of that, the bonding is occurring here. So there is no macroscopic deformation. Microscopically, there will be deformation, but macroscopic level, there will not be any deformation in this process. and there is no solid filler metal or may not be inserted here, but in some cases they will insert the. So this is schematic representation. This is the diffusion bonding furnace inside. So two materials, A is one material, B is one material. They will be stacked like this, and it will be heated. By heating, the atoms will move from this side to that side, from A to B and B to A. So this is the principle, diffusion bonding working principle. So any surface. So here it is surface to surface contact, not edge to edge. Mainly, this process is used for surface to surface bonding. So any surface, whatever the polishing method you use, there will be some asperities. Asperities means ups and downs, peaks and valleys on the surface. Roughness will be there. It is very difficult to produce surface finish to the tune of optical clad. So all the surfaces, they have some ups and downs, the peaks and valleys. So in this initial stage, so there is a contact between the peaks, and the valleys are there is no contact between the valleys, so there is a vacant site here. But in the peak point, there is a contact. So this is the first stage. So here, when you heat this material, so and also you need to apply load, and because the combination of thermal energy and the mechanical energy, so the contact points will get deformation. Deformation will occur at the interface. Interface between the top surface and the bottom surface. In the second stage, because it's a continuous process, it will take longer time. And there is a second stage, the grind boundary migration will happen like this. The grind boundaries will move, and there is a pore elimination. What are the pores? These are all the pores. Pores means there's a gap between the top surface and the bottom surface. So that will be because of movement of the grind boundary, migration of the grind boundary, the pores will be closed slowly. And third stage, once this is closed, then atoms are free to move from volume diffusion and pore elimination will occur in the third stage. This is occurring in the third stage. And in the diffusion bonding, you have two types of diffusion bonding. One is solid phase diffusion bonding, other one is liquid phase diffusion bonding. In the solid phase diffusion bonding, there is no melting at all here. In the liquid phase diffusion bonding, they use interlayers. Interlayers are low melting materials. Then that interlayers will melt. So that's why they are calling it the liquid phase diffusion bonding method. So solid phase diffusion bonding, it's you required normally both the diffusion bonding, you require a vacuum atmosphere. The air will be completely sucked out. Vacuum should be maintained, and the heat being supplied by the induction heating and pressure. So these are the main things. So you require vacuum, you require heating, you require pressure. Then the process requires a good surface finish on the metal surface, normally in the range of 0.4 microns. The surface finish should be 0.4 microns, and surface should be as clean as actually possible. And then this is a simple setup we have, a low temperature diffusion bonding machine. It's available in our center. And this is the furnace, and this is the loading unit here. So normally the specimens will be stacked like this. You have the lower die and the upper die, and the specimens will be stacked one over the other. This is one material, and this is another material. And this will be stacked, and through this top plate, the load will be applied, the load will be transferred onto the materials to be joined. There's a small clipping animation. You can see first they are stacking the metal. You can stack any number of metal plates. It is based on the furnace volume. So now dynamic load and heat are applied. So when the heat and the load is applied, you see that the grinds are migrating. Migration of grinds and closure of the pores. And once it is closed, then you will not see two different materials. So this is an example for the similar materials. So the liquid phase bonding is applicable for dissimilar material combination because dissimilar material, as I told you, so there is a difference in melting point. So the melting point differs. For example, suppose I want to join aluminium with stainless steel. Aluminium is the melting point is 650 degrees centigrade, but the stainless steel, the melting point is 1550 degrees centigrade. So enormous difference, nearly 900 degrees centigrade difference. So if you heat at 700 degrees centigrade, aluminium will melt. But if you don't heat to that temperature, what will happen? Nothing will happen to the stainless steel. So in that case, they use a dissimilar inserts they will use. The inserts are normally silver. Silver will be used. Sometimes copper also will be used. The low melting inserts will be used in between the two different materials. So that inserts will melt, and that when the melting of inserts will make the inserts in the liquid state, and they will spread into the both the surfaces of the top plate and the bottom plate, like bracing, how it happens in the bracing. So this is called liquid phase diffusion bonding. So here there is no melting in the materials to be joined. Only the inserts, which is at low temperature, low melting material, they will melt. So that's why it's called liquid phase diffusion bonding. So here this is the interlayer. They will keep like this, and the second stage interlayer melts, and the third stage it is the heterogeneously the bonding method, and the molten interlayer will spread both the sides, and it will cause the bonding between the two materials. And by using this process, you can join not only the metals and alloys, you can join metals with ceramics also. So it's you see that this is the top portion is the ceramic, and the bottom portion is the metal. So when you heat the metal and ceramics and also apply the load, the metal will get deformed. So metal will get deformed, and that will flow, and that will flow closely. That slowly they will occupy the vacant spaces. If you see that the ceramic will not deform, ceramic will be as it is. Only the metal will be deformed, and it is joining, bonding with the ceramics. So this is one viable method to join ceramics to metals. And there are a lot of criteria that should be considered for diffusion bonding. Surface roughness, it should be 0.4 microns. Bonding pressure, it should not be high, it should be high enough, but it should not exceed the yield strength of the material. Because the bonding pressure exceeds the yield strength of the material, then the deformation will occur. So you should maintain the pressure well below the yield stress. And the bonding temperature, another parameters, important parameters, bonding temperature, it is decided by the recrystallization temperature. Normally, it will be kept in between 50 to 70% of melting point. So this melting point is based on the lowest melting point of material. So if you have aluminum and copper, so you have to take the melting point of aluminum for consideration. So from the aluminum melting point, you have to use 50 to 70% of the melting temperature. Holding time, it is normally to vary from 30 minutes to even 3 hours also it will take. So it's a long process, it's a slow process, but some of the components which cannot be joined by conventional diffusion welding method or conventional any other methods, you can join by using this method, though it is very slow. The productivity is very, very low, so it is a slow process, but it is required in some of the applications. So one case study I will show that we did a lot of work on the aluminum, joining aluminum alloy with magnesium alloy, and so this is aluminum alloy. The big challenge in aluminum and magnesium, both are non-ferrous materials. You know that, okay? Both are non-ferrous metals category, and at the same time, both are lighter in weight, and both will have the melting point. If you see the melting point almost equal, 600 degree to 650 degrees centigrade. There is no difference, not much difference in the melting point. But it is very, very difficult to join these two alloys, aluminum alloys and magnesium alloys. The reason is the crystal structure. Crystal structure is different. Aluminum alloy, the crystal structure is FCC, face-centered cubic crystal structure. But magnesium alloy, it is SCP, hexagonally close-packed crystal structure. Okay, so the density is almost same. It is aluminum alloy is 2.7 and magnesium alloy is 1.7. Density is almost same. Melting point, magnesium alloy is 600 and aluminum alloy is 650 degrees centigrade. It's also same, but the main problem is, which is not allowing the material to join, is the crystal structure. The crystal structure is different, so they are not compatible. So only the diffusion bonding is one viable method to join these two. So here we did a lot of experiments. We varied the temperature in this effect of temperature 400, 430, 460 degrees centigrade. You can see the difference. So when you use 400 degrees centigrade, it is bonded to the aluminum and magnesium sheets, but at the interface there is no interlayer, diffusion layer. It's called diffusion layer. But here you can see the diffusion layer, the white color layer. It's called the diffusion layer. This forms mainly because of atoms moving from magnesium to aluminum, aluminum to magnesium. They meet here, and they form a layer. That layer is called diffusion layer. If you increase the temperature, the width of the layer is increasing. Okay, so these two, no diffusion layer, this is also weak, and too much of diffusion layer, it is also weak because the diffusion layer is intermetallic, they are brittle in nature, the bonding strength is lower here. But the medium, so here the strength will be higher. So one need to optimize at which temperature, at which pressure, at what time you are getting the maximum bonding strength. So you see that at the interface, the hardness is very high. This is aluminum side, this is the magnesium side. And the interface, because of the diffusion layer, intermetallics forms, a lot of phases, complex phases forms, the hardness is high here. So this is the XRD, and you can see these are the phases will form in both the sides. So for this condition, there is the AZ31B and the 6061 Li, we joined by using diffusion method, and we did a lot of trials, and we found that at 430 degrees centigrade and pressure of 50 megapascal and holding time of 30 minutes is found to be optimum. That optimum means under this condition, the joints which are made under this condition, they yield at maximum bonding strength. And there are many combinations of materials available, and the people are doing it with the different. But if you see that all of them are done at the vacuum. So vacuum is a must one. So normally 10 power minus 5 parts they will use at the vacuum level. And a lot of applications in the aerospace industries, many applications are there in the aerospace industries because it uses aluminum alloy, titanium alloy, nickel-based alloys are used. So there are a lot of locations, components there. You need to join these two different materials. And a small clipping, video clipping, you can understand the.
There's been a huge resurgence of interest in diffusion bonding in TWI. Indeed, it's invested in a rather unusual machine to do just that, on longitudinal section. As Alec Gunner explains, we've been diffusion bonding here at TWI for the last 41 years now. In the early days, there was obviously a lot of interest about what this technique might get to deliver. And for a long time, it was a solution looking for a problem. However, the recent developments coincide with increased advances in fields such as aerospace, and now this is a technique which is being seriously considered because it has the potential to deliver a particularly good joint. It's a very simple process. The equipment is really not a lot more than a hot box with a press running through it. It works on the principle that if you heat components up to the point where the atoms on the surface have enough energy to start jumping across the gap, then they will bond together. So you would take two components with a very good surface and you push them together and heat them up and wait. You form a bond which is metallurgically perfect. If you took a section through that bond and polished it, then if you've got the conditions right, you won't be able to see where the bond line is. And if you then did tensile testing, you would expect the failure to occur in the parent rather than the joint. The new machine is a bit different. Most machines work with a vertical press. This machine has been built with side ports so that we can put the extension tubes on and swing it around horizontally. And that way, we're not really limited
to temperature. Load will be applied.
Put longer and longer side pieces on
load is applied.
Components. So things like tubes or rods or bars.
Measure the temperature.
It's a slow process compared with arc welding. You're very unlikely to be able to complete.
So furnace. Inside the furnace, they are stacking the two plates to be joined.
Unique advantages. So, for example,
closing it, it's completely closed, and the suction pump is used to evacuate all the air from there.
We're finding that there's interest in heat exchangers, there's interest in various aerospace components, aircraft brakes that have
bonding is lower
for a long time now. They're looking into other areas, past turbines. There's also other interests in terms of long components which can't be manufactured in the lengths needed, and this allows the closest thing.
So this is how the diffusion bonding works, but the video completed within 1 minute, but it will take the normal diffusion bonding cycle will take a minimum of 6 hours. Heating will take some 1 to 2 hours, and then you have to maintain the temperature for at least for 30 minutes to 1 hour. Then cooling will take another 2 hours. So totally in 6 hours for one cycle it will take. It's a very slow process, but no other way. In some of the components, some of the materials are joined even today using the diffusion bonding process. So next one is very quick process, just opposite to the diffusion bonding. It's called the explosive bonding. Though it is a very old process, it has many applications in the defense applications concerned. So explosive welding is the energy is produced by the chemical energy. Let's say explosives are chemical substances. That the energy available in the chemical substances are used to make this bond. So the bonding between the two materials, whether it's similar or dissimilar materials, it's a metallurgical bond it will produce. And quality of the explosive produced weld primarily depends on the state of the interface between the components. And there are two setups normally people use, and we also did a lot of work on this explosive welding. Now we are not doing it. So earlier we did a lot of work on this. So there is a base plate and there is a flyer plate, and above that, so base plate is one plate. You have two materials to be joined. Maybe this is, you can take it as a steel, carbon steel, and this flyer plate you can take it as aluminum alloy. You want to join these two. So over the flyer plate, you have to pack the explosives. So there are a variety of explosives are available based on the velocity, detonation velocity of the explosives, and based on the weight of the explosives. There is a ratio between the explosives and the flyer plate, E by M ratio. E is weight of the explosive, and M is the weight of the flyer plate. So if you know the weight of the flyer plate, so using that ratio, you can find out how much explosives is required. So that explosive you have to take, and that will be packed throughout the entire area of the flyer plate. And then one end you have to keep the detonator. So detonator also, you have seen that it is a small capsule, aluminum capsule. Inside the aluminum capsule, you have the explosive, high explosives. And so this detonator is having two the wires. That wire is connected to a battery. That battery is a charged battery. You can operate from 100 meters or 50 meters away from it. You cannot operate from standing close to that. And another thing is you have to keep some distance between the bottom plate and the flyer plate. So that distance is known as the standoff distance. So there for the standoff distance, again it is having a relationship with the flyer plate thickness. Thickness of the flyer plate will decide how much standoff distance you have to keep. Whether it is a 0.6 or 1 or 2 times the flyer thickness, it depends on the material. What is the flyer material and what is the explosive you are using. These data are established for many materials, many combinations. It has been established. This is the parallel setup, and the inclined setup is they will keep the flyer plate with the inclination 30 degrees or 45 degrees inclination. Same method they can use. And this is what will happen during explosion. When the detonator is ignited, the detonator will ignite the explosives, and the flyer plate is accelerated. This is the clad layer, that's the flyer plate. And then once the explosive is exploded, and that will make the flyer plate to accelerate at high velocity to impinge or to collide, to hit on the top surface of the bottom plate. When they hit, a lot of pressure will be produced here, and there is a jet at the interface. There will be a jet will be produced. That jet will remove, due to the collision, there is a jet velocity will be produced. That jet is removing all the layers, the surface layers. Even if it is any rust or any oxide presence on the surface, that will be removed by this jet. This jet is produced mainly because of the collision between the flyer plate and the base metal plate, because the collision is not as a small collision, it's a very high velocity collision. And this is what happens at the interface. So because of the collision, the material at the collision point will undergo it, will behave as a fluid, that's a highly compressive fluid. But in the solid state itself, they will behave as a fluid. Because of this fluid, so some of the material will deform. The bottom plate will deform like this, and the top plate will deform like this. So there is the entrapment of bottom plate material and the entrapment of the top plate material from. So they are producing a mechanical locking type of things. So this is happening during the collision. And you can see that small animation, you can understand. So, explosive is packed and detonator is placed here. Inclined surface is a standoff distance. And now detonator is operated. So this is producing the bonding. And you can understand it's in another clipping.
With a strength measured in millions of pounds per square inch, explosion welding can accomplish what no other welding method can. Join nearly every kind of metal combination,
Two plates.
no matter type or composition. To create an explosion weld,
See, you can join very huge plate like this in one shot.
then covered with a high-powered explosive.
So the explosives are spread
When
here.
detonated, the downward force of the explosion welds the two pieces together through a combination of intense force and remarkable physics. The explosion welding process begins as soon as the two metal plates arrive at DMC's production facilities. To maximize the welding force of the explosion, the surfaces of each plate are ground as uniformly flat as possible, a process that also removes any rust, oxides, and other surface fluids. They are then ready to be assembled into the pack, which locks the plates in position for the explosion. To build a pack, the stronger and thicker of the two plates is laid face up. From now on, this plate will be identified as the back.
So they are maintaining the
Small
standoff
metal
distance.
spacers of equal height are then tacked onto the surface of the backer in a uniform grid. These spacers will maintain a set gap between the backer and the second plate, which is placed on top. This second plate is thinner than the backer and is called the clad. The standoff gap between the backer and cladder is less than an inch in height, yet without it, the explosion weld would be impossible. DMC uses an
So
explosive
the standoff
product that is a
distances
proprietary
must, you have to maintain some standoff distance
explosive
between
chemical.
the top plate and the
The
bottom.
amount and exact formulation is always matched.
So the
to the types
explosives,
of
they are
metals
packing
involved.
of
Once the pack
explosives.
is set, the explosion is initiated at one end of the clad and moves across the upper level of the pack at a uniform speed. This explosive front progressively drives the cladder plate downward toward the backer at the slight collision angle caused by the standoff gap. Forward of the collision point, air is forced out of the gap at high velocity. All oxides and impurities are expelled,
It is the
rendering the plate
expulsion of
surfaces
oxide rays.
metallurgically pure and ideal for a weld. As the backer and cladder collide, the weld is
It's
created
animation
nearly
basically.
instantaneously across the entire surface of the plate.
Yeah. So another animation, you can see how the surface layers are removed. Because of the pollution of the interface, as I told you, a lot of energy is produced, and these particles, vector particles which are coming out, they are all the oxide particles which is removed from the top surface of the fire plate and the bottom plate, base plate. So at the collision point, you will get this type of a jet. It is called in the explosive welding, it is called the wavy interface. This interface is a typical characteristics feature of explosive welding or explosive bonding component. In all the good explosive welding bonds, you will find at the interface, you will find this type of wavy interface. So like this is actual micrograph. This is aluminum alloy. This is the copper alloy. So you will get this type of wavy interface. So this is from this point to this point. It is called as the wavelength, and this is the thing plus. So this is the amplitude of this wave. So the amplitude of the wave will decide the bonding strength. If it is amplitude is higher, then the bonding strength will be larger. And there are many parameters to control. So type of explosive, what explosive you are using, low explosive, medium explosive, high explosive, that depends on the detonation velocity. And explosive loading, which I told you, E by M, the mass of the explosive to the mass of the fire plate, and collision point velocity, collision angle, 30 degrees, 45 degrees, 60 degrees, and thickness of the fire plate, and the standoff distance, how much standoff distance you are keeping, whether you are keeping 1 mm or 1.5 mm or 2 mm. And then fire velocity, thickness of parent plate, that's also will play. And angle and surface finish, they all will play. But majority, this explosive, types of explosive loading and the collision angle, flare plate thickness, standoff distance, these 5 parameters will play a predominant role on the explosive cladding than the other parameters. So there are different types of explosives available today in the market. RDX, you hear about in the movies also, you hear about RDX, PETN, TNT, trinitrotoluene, ethyl, leadazide, data sheet, ammonium nitride, special gelatin. This special gelatin is the low explosive, which is very common. If you go to any quarries, to the Kalakurchi or Salem side, you will find a lot of quarries, they use this special gelatin. Ammonium nitride, this you can develop in the chemical lab, you can develop this ammonium nitride. So these are all in the 2000 to 3000, they will be called as the low explosives, meters per second. Okay, even the low explosives, lowest explosive, which is special gelatin, if you see that the velocity is 2000 meters per second, that means what? In 1 second, it will travel at the speed of the detonation velocity is 2 kilometers per second. It's a huge speed. But if you take high explosives, RDX, PETN, TNT, more than 7,000 meters per second, they are all high explosives. In between, leadazide and other things comes under the medium explosives. So this is one small example which shows that this is the velocity. Sorry, the slide is not so clear. Velocity is 1,800 meters per second. Here it is 2,100 meters per second, 2,500 meters per second. So the detonation velocity increases. You see that interface. It's a low velocity. There is no wavy interface. Okay, it's the highest velocity. We have a lot of the wavy interfaces, very coarse. We can say it is a coarse wavy interface because there are a lot of peaks here. But this is the optimum condition because in unit length, if you take in 1 centimeter, the number of amplitudes, waves are more in number. So here, the bonding between these two surfaces will be higher than this or this or this condition. So this is the ideal condition or preferred condition or optimum condition that you one need to produce. So this will give a maximum bonding strength. So that the parameters which produce this type of wavy interface, that means in a unit distance, you should have the more number of waves or wave amplitudes. So then that will give more bonding. That's the concept of this explosive cladding. So these are the combinations of clads. The black regions are already joined, aluminum with aluminum, aluminum with nickel, aluminum with copper, they are joined. Only these white regions are not yet joined, people not yet explored, and one can interested in explosive welding, you can think of joining aluminum alloy with zirconium, copper alloys with zirconium, stainless steels with molybdenum. These are the combinations not yet tried, not yet researched. So that is the scope for the research or in the explosive cladding. So many advantages. We can join similar materials, steel with steel, or dissimilar materials, steel with aluminum, steel with copper. You can join. Weld area you have seen in the video is not. There is no restriction. You can do a big plate. It's even 10 meters by 10 meter. You can join in one shot. And the metals having different melting point. There's no need to worry about melting point. And no need to worry about the crystal structure. Nothing will, there is no limitations in this process. Only problem in this process is, there is a limitation is the material to be joined that should have some amount of ductility. Because the brittle materials is difficult to join. Why the brittle materials are difficult to join? Because due to the high explosion, high collision velocity, the brittle materials will go into pieces. So that is the only requirement. The materials to be joined, that should have some amount of minimum ductility that should have. If you have ductility, small amount of ductility, okay, so something around 10% and more, you can join using this process very effectively. So there are many applications this explosive welding can be used, and some of the components produced by explosive welding. Here, not only 2 plates, you can join 2-3 plates. Okay, this starting from aluminum, and then it's stainless steel, and then carbon steel, like that. Any number of plates you can join in one shot. That is the advantage. So, like this, dooms. you can form and then weld. There is a process called form cladding. So, Annamalai University, in the Department of Manufacturing, we did a lot of work on the form cladding. In one shot, you can form as well as you can bond. The material can be joined. So, in India, even in now, this process is very widely used in the defense DRDO. In Chandigarh, there is a center called TBRL. So, they are doing a lot of work on this explosive cladding. In other places, the problem is getting license, because if you want to store the explosives, you need to have the license. Getting license is a big problem, and there are a lot of norms and conditions to store the explosives. That's why not many people are working on this process. So the next process is magnetic pulse welding. This is also high velocity welding process. It is entirely different. There, in the explosive welding, it's almost like explosive welding. Only difference is there we use chemical energy in the form of chemical substance, that's explosives. But here, that energy, that high energy, is produced by the electric energies. So the capacitors and other things are used to produce high voltage, and that voltage will be applied a short period of time. And here also you can join similar and dissimilar materials, and here also you can get the metallurgical bond. So there are, you can join sheets and you can join the tubes. One thing is, the very important thing here is the magnetic coils. The magnetic coils are made by the copper coils, and the design of the configuration and design of the coils is very, very critical in this process. So that is the only challenge in this process. The coil is the design and fabrication of the coil for each component. You have to design a coil. You have to fabricate a coil. You cannot use one coil for all the components, all the sheets or all the tubes. So for each tubes or each sheets, you have to have the one coil is required. It's a consumable. And this is a schematic diagram where the magnetic, how it works. So this is one tube, outer workpiece. You can take it as the aluminum, and this is the copper. And in between there is a gap, like it's called the standard distance again. And this is the copper coil, both the sides. The energy will be supplied through this charger and capacitor banks. And then there will be short pulse, will be supplied. And because of the high voltage, the outer workpiece is moved or accelerated towards the bottom workpiece, inner workpiece. During that time, high pollution occurs. Other things are same, like explosive welding, pollution, everything is same. Only thing is, there they are using explosive chemical substance. Here they are supplying high voltage to accelerate the fire rate. And you can understand here, you see this simulation, you can understand here how it is happening. The bonding is taking place here. And so this is the copper coil. For tubes, you should have the copper coil should be in this shape. And this is the prayer tube, and this is the mandrel, that is the inside material. You have to give a support inside. That's called the mandrel. You need to use that. This is the copper coil, maroon color, and this is a outer prayer plate, and this is the inner tube. So that should be joined. So the interface will have this type of, similar to the explosive welding, we have the wavy interface. And you can see the clippings here, how it works. The capacitors and switch, which is used to produce high voltage, to supply high voltage. So they want to join these two. This is the aluminum tube and the steel former. They want to join. This is the tube and this is the steel former. This is aluminum, this is steel. And this is the magnetic coil, which is inside, and we have this covering. A small flash will come. If you observe closely, once you switch it on, a small flash will come. Yes, that's all, over. So it's bonding is over. And this is the before bonding, this is the after bonding. Yeah, I'll move to that because the similar one, slightly different. In India, so the magnetic pulse welding, there's only one industry is having this machine. in Bangalore, in the Pune Industrial Estate. Industry name is MacPulse Technologies. In Pune Industrial Estate, you can find out the MacPulse Technologies. He is having a huge machine, imported machine from France. And otherwise, BRC, Bob Atomic Research Center, they are also using this process, and they are also developing low-cost machines, magnetic pulse welding machines. These are the microstructure at the interface: copper with brass. This copper, this is brass, and copper similar metal. You will get a very good in the wavy interface you can get, and stainless steel to stainless steel, and this is aluminum to steel. And parameters concern voltage, standoff distance, working length, and fire thickness. Working length is the overlapping length. How much is the overlapping length? Not the entire tube is bonded together. Only the overlapping length is known as the working length. These are the parameters, important parameters here. So many advantages: highly repeatable, high speed, dissimilar metals are possible, no need of filler metals, green, clean, high quality, and low cost, high productivity. If it is automated, you will produce very large number of. There are a lot of applications in automobiles, and it's finding a lot of applications in the automobile components. And the last topic, maybe not last, it's okay, it's the last topic: friction stir welding. And friction stir welding also is used enormously for the dissimilar material joint. I think you hear about a lot about the friction stir welding process. I don't want to tell about the background of this process. It is a solid state welding process. It is a solid state welding process. There is no need of filler metals, no need of shielding gases. There is no need of edge preparation to join, as in the case of what we do in the fusion welding process. So it is an environmentally cleaner process because no smoke, no fumes, no glare, and it comes under the environmentally cleaner welding process. So this is a schematic diagram. It's normally used to explain how this process works. So there is a tool. It is the heart of the process. The tool is harder than the material to be joined. If you want to join aluminum alloys, then you can take high-speed steel as a tool material. And the tool will have three portions. This is the shank portion, and below that there is a shoulder portion. This is, and below the shoulder portion is a small portion called pin portion. So these dimensions are very critical indeed to get the successful joint, because the pin diameter should be normally equal to the thickness of the plate to be joined, and the pin length is 0.5 millimeter or 1 millimeter shorter than the thickness of the plate. So based on the thickness of the plate, you have to design the tools. So the thickness of the plate to be joined, that will decide the tool dimensions. So pin length is 0.5 millimeter shorter than the plate to be joined, and the pin diameter is equal to the thickness of the plate, and the shoulder diameter is 3 times the thickness of the plate. So the plate thickness will decide what is the pin diameter, what is the shoulder diameter, what is the pin length. All those things will be decided. And this slide will show you how it works. So you have to make the tool. The tool will be fitted to the machine. You fix up the speed, what speed you want to rotate, 1000 RPM, 1500 RPM. Then start the machine, bring down the tool, establish contact between the two surfaces here, and the pin first will establish contact with the top surface. So smaller area comes under friction. Friction produces heat. Heat produces the plastic deformation of the material. Then further plunging, the downward force, the shoulder area comes in contact. So larger contact area, larger heat friction, larger heat generation, large amount of metal is deformed here. So when you do this, the metal will flow from one end to other end. So like this, it moves. Then you move the tool forward, you will get the bonding here. So this is the stages of. So how it works in the animation. So welding, tool rotates, plunging, welding, and then retract the tool. So this is how it works. So the shoulder produces maximum heat. 2/3 of heat will be produced by the shoulder, obviously because it has large diameter. The probe, that's a pin. Pin will produce a minimum heat, but it's not for heat produced production. It is for stirring purpose. Pin is mainly for stirring the material. So this is this process, though comes under welding, but basically it is a metal forming process. Extrusion and forging combinedly will take place during this process. Extrusion and forging process will take place combinedly in this process. And this is the machine which we made in 2003. First machine, I can say it is it's not a retrofitted machine. It looks like a vertical milling machine, but we did using the ACT one in 2004 itself. And another machine in 2008 we fabricated. It is the CNC control machine. The first one is the fully manual control, and this is the CNC control machine. And now a lot of welding is done. So there is a difference between aluminum alloy and steel. This is looking at the picture. This is aluminum welding. This is steel welding. Okay. So the tool is a challenge here in welding the steels. Right. So the friction welding process now, as on date, is a very good process. The best process, I can say, it's the best process for joining aluminum alloys, magnesium alloys, copper-based alloys, because there is a boundary less than 1000 degrees centigrade melting point. The melting point of material is 1000 degrees centigrade, and less than that, it is the best process, friction welding. But above 1000 degrees and 1000 and other degree, it has potential, but the main problem is tool material. The tool material is the big challenge here. And there are many parameters: rotational speed of the tool, welding speed, axial force, and tool parameter, tool pin profile, tool shoulder diameter. Similarly, base material also, tool material hardness, base material, and the yield strength. This all will affect the quality of the weld. There are many relationships, equations are there to calculate the heat generation during welding. This is the old one, and first one I can say Guriter et al. They developed. Why I am showing this equation is to explain the effect of each parameter on the heat generation. So if you look into this, S is the welding speed, and mu is the coefficient of friction, P is the axial force, omega is the rotation speed, and this is the shoulder radius. So out of all the parameters, the welding speed, which is in denominator, that is having inversely proportional relationship with the heat generation. All other parameters are in numerator, they are having directly proportional relationship with the heat generation. If these parameters are higher, then the heat generation will be higher. If these parameters are lower, then the heat generation will be lower. But here in the welding speed, it is opposite. Welding speed is faster, heat generation will be lower. Welding speed is slower, heat generation will be faster, opposite effect. So based on this, it is also known in this process we need to optimize the parameters. Then only, so there are other defects, aluminum alloy, magnesium alloy, in fusion welding, TIG welding, MIG welding, they produce a lot of defects, solidification related defects, hot cracking, alloy segregation, partially melted zone, porosity. These are the defects in fusion welding of aluminum alloys or magnesium alloys. But in the FSW, friction welding, those solidification related problems are completely eliminated because there is no melting here. It is a solid state welding process. Welding takes place well below the melting temperature. So hot cracking, alloy segregation, partially melted zone, porosity, those problems are completely eliminated. But this FSW is having its own problems. These are given here. If you use high heat generation, if you use these parameters, okay, you will get high heat generation. They will produce these defects: coarsening, precipitates, flash formation, piping defect, another defect. Low heat generation will also produce some defects. So one need to optimize these parameters. Then only you will get proper material flow. Then only you will get the good conservation of the metal, and you will get the defect-free welds. And one case study I want to show for the dissimilar, because the topic is dissimilar non-ferrous alloys. We joined here 6061 with the AU31B, and I told no, it's very, very difficult by fusion welding process. TIG welding, when you do TIG welding, lot of intermetallic compounds will be formed at the interface. So immediately after welding, you can break by hand by just bending it. The joints will come out to two pieces because of the formation of the intermetallic. As I told you, aluminum alloys are FCC and magnesium alloys are SCP metal. They will not mix together. They will not mix together. And this is the larger spectrum of the microstructure of the interface, intermetallic layers. And this here we did using FSW. In the advancing side, we used 6061, and retreating side, we use the negation. What is advancing side and what is retreating side? Many people will get confused. Okay, if you look into this picture, the tool is rotating. In which direction it rotates? It rotates in clockwise direction. Okay, the tool is rotating in the clockwise direction, and the tool is moving forward from here to here. It is moving forward direction. So the tool velocity, rotation velocity vector, and the tool traverse speed vector are both in the same side. The left side is the advancing side, and the right side is the retreating side. Suppose if I change the direction of welding, then advancing side will come here and retreating side will come here. So please remember the tool rotation velocity vector and the tool traverse speed velocity vector both should be in same. If it is in same direction, then left side is on your left, it is advancing side. On your right, it is the retreating side. So normally, when you go for the dissimilar welding, advancing side you keep the harder material, stronger material, high strength material. On the retreating side, you keep the low hardness, low strength, and the low strength material keep in the retreating side. And we welded aluminum with aluminum. This joint, this is magnesium with magnesium. Second one, aluminum and magnesium both joints we made using this process. And this is the comparison. You see aluminum similar joint, we got 244 megapascal tensile strength, and the magnesium alloy 200 megapascal. And dissimilar, we got only 140. Even it is better because you will not get in any other process, you will not get this much strength other than friction welding process. So this is the macro structure in similar welding, aluminum with aluminum. So you will see that inverted trapezoid shape friction still processing zone. Here it is a bell shaped friction still processing zone in magnesium alloy. In dissimilar joint, aluminum with magnesium, you see that this is a shape that's a straight cylindrical region, and I'll show in the magnified view. So this is here. Mixing takes place, but layer by layer. So you see here, aluminum with aluminum, magnesium with magnesium, these two are similar. But in dissimilar, you see that intercalated microstructure. This is known as the intercalated microstructure. The dark region is magnesium and white region is aluminum alloy. So one layer is aluminum, and the next layer is magnesium. Like that, they will form. There will not be proper bonding, but there is a mechanical bonding took place because of this stirring action. And this is the TM, electron TM micrograph. So the precipitates are fine here, uniformly distributed here also, but in the dissimilar welding, there's a lot of intermetallics. You can see Al2, Mg17, and all those things will occur here. That reduces the strength. And but successfully we welded, and it is giving 40% lower than the aluminum alloy, 30% lower than magnesium alloy, but we are able to achieve 140 megapascal tensile strength in the dissimilar joint. And finally, it's a linear friction welding, another process. It's a variant of friction steel welding. As I told you, it's a welding of steels, welding of titanium alloys, friction steel welding of steels, friction steel welding of titanium alloys, friction steel welding of nickel-based alloys. It is highly challenging, mainly because of tools. For aluminum, magnesium, copper, you can use high-speed steel. For steels, titanium and other things, you have to go for the tungsten-based alloys, or tungsten-rhenium-based alloys, or PCBM tools. They are very expensive tools, expensive proportion. So when you want to join this high-strength material, high-melting materials, then you need to avoid the tools. Then this process, linear friction welding, is developed. So this in the linear friction welding, it's entirely different from the friction. There is no tool here. First of all, there is no tool. It is like a rotary friction welding. Rotary friction welding, you use the cylindrical component. Here you use the any profile you can use here. Here it is no rotation here. It is only oscillating. It's a reciprocating motion. This is reciprocating. It will reciprocate at a very high frequency. And here it is stationary one, and the forging force, axial force will apply to the stationary workpiece. I'll show the clipping. You can understand this is a machine. We have a machine. It's a linear friction welding machine.
How does linear friction welding work? basically by forcing together pieces to be joined in such a way that linear motion and pressure are converted into heat, which literally bonds the pieces into one part. Two pieces to be joined are aligned in a linear friction welding machine. One piece is held stationary, the other is oscillated rapidly using a linear actuator. When the linear actuator reaches a
reciprocating, this is stationary.
amplitude of oscillation,
Axial
the
force
moving
is
piece
applied.
is forced against the stationary piece. Friction between the parts heats the budding surfaces to forging temperature while displacing parent material. The force that is applied during the process can be varied to optimize the resulting welded component, and these forces are maintained for a specific amount of time or a specific amount of displacement. Once one of these two desired criteria is satisfied, the oscillation stops, the moving piece is returned to the mid-stroke of oscillation as the oscillation is stopped.
So this is the macro section. It's a best process for joining titanium-based alloys, especially in the gas turbine. The blade and disc components are made using this linear friction welding process. We are also doing. We have machine in our center linear friction welding. I think we are in the 1A1. We have the linear friction welding machine right now, and we are in the process of making a lot of work on this process using this process. It will also give very good joint efficiency. You see that ultimate tensile strength. The base metal is 659, joint is 542. 82% of base metal strength we are able to achieve by using this process. And the slow motion, you can understand how it works. It's one is reciprocating top one, and this is the stationary one. It's a very slow speed, slow motion. It's not slow speed. You can understand how the deformation occurs and the flash forms is all due to friction. Due to friction, heat is generated. The heat, that's the thermal energy, and the mechanical force, that's the downward force, both causes metal to deform from one plate to other plate. So by that, there's no welding here. It is only in solid state. It's a red hot condition. Let's say it's a red hot condition. This bonding is occurred. Then suddenly the stationary piece will be forced, the forging force or axial force will be applied from here. Then it is allowed to cool, allowed to solidify. Then this joint is completed. So finally, I'll take only 2 or 5 minutes to show the profile of my center, profile of C major, and this is in the center. We have 11 laboratories and one group, one building. We have all this 3-story building. We have all this 11 laboratories here. The center has completed 40 R&D projects sponsored by DST, DRDO, ISRO, DAE, many agencies, worth of 10 crores and total project cost. And 5 projects are ongoing, worth of 2 crores. And center has published more than 370 papers in Scopus Index journals alone. And the center has produced 40 PhD. And our first area is materials joining. Not only material joining, we are working on surface engineering, and we are working on newer materials development. And these are the facilities in materials joining. We have almost all the welding processes except the electron beam welding process. And these are the photograph of those welding machines. And most of them are in working condition. And the majority of major facilities in surface engineering, it's a coating, thermal spraying, nano coatings. We have very good thermal spray lab, plasma spraying, HO spraying, power flame spraying, wire spraying, and PVD, CVD, and we have very good tribology lab, corrosion testing lab, and there are recently developed nano coatings lab also. We have EV, and sputtering, and this is the photograph of those machines and the equipments. And for testing and characterization also, we have very good facilities except TEM. We have all other facilities. SEM we have, SEM with EDS we have, and XRD, of course, in the university physics department we have XRD. And these are the facilities available to test and characterize the materials. And a piece of information, those who are interested in welding, because my topic is on welding. So we introduced a program, MB Welding Engineering Program, 2 years course, full-time program with industry partnership. 2000. The difference between other MB Welding program and our program is Out of 2 years, 1 year the students will be in Annamalai University. They will complete all the theory subjects, labs, everything in 2 semesters. The third semester and fourth semester, that is in second year, the students will be sent to the industry. We have a tie-up with some 12 industries, more than 12 industries. We will send the students to the industry. The students will do the project, industry-driven problem. They will take the industry-driven problem. They will stay there in the industry. They will work there, and they will only come to the Annamalai University only for the progress review meeting. Otherwise, they will be doing there, and after the end of 1 year, they will submit the project report, and the degree will be awarded. So with the ME Welding degree, with the degree, they have 1 year industry experience. They will get the 1 year industry experience. During that period, they will get a stipend. In the first year, they will get 5,000 rupees of stipend. In the second year, the industry will pay the stipend based on the industry norms. Some industries are paying 12,000 per month. Some industries are paying 8,000. Some of them are paying 6,000 per month as a stipend. So, if anybody interested, the final year students, they can contact me for further information. And these details are available. This is my contact, mobile number, and the email ID, and also this is the website address of our in the Annamalai University website. You can find the details about the center, C major. The C major profile, complete profile you can see from the Annamalai University website. Under the centers, the C major is there. So you can note down or. So thank you for your passion listening. I think I took 1 hour and 15 minutes. So 3:05 I started, and 1 hour 15 minutes I tried to cover. Any clarifications, any questions? Not only on the topic which I covered today, maybe any general questions related to materials joining, you can ask. You are free to ask. Thank you for your passion listening.
Sir, first of all, thank you very much, sir. Thank you so very much for this presentation. So, let me look into some questions, sir. Sir, Mr. Sandeep Kumar had asked this question. Sir, is it possible to weld magnesium alloys by FSW process?
Magnesium alloy.
Yes, sir.
Magnesium alloy with magnesium alloy.
Sir, simply he asked magnesium alloy.
Okay, it's very, very easy. This is the friction stir welding is the best process for welding magnesium alloys. You cannot weld it by TIG welding, MIG welding, because MIG welding you require filler metal. Even in TIG welding, if the thickness of the magnesium alloy sheet is higher, then you have to require filler wire. Filler is the problem for welding magnesium alloys. Getting filler wire is the problem, because the reason is the magnesium alloys basically they are the elongation. I can say that's ductility of the magnesium alloys very low when compared to aluminum alloys. Aluminum alloys you have elongation 20%, 25%, 30%, but magnesium alloy will have elongation in the order of 8 to 10 or 12%. So elongation is limited. So because of ductility is limited, making wires are difficult in the magnesium alloy. But people are making magnesium wires now. But when compared to the fusion welding process, what are the processes you can take? Friction stir welding is ideally suited for any grades of magnesium alloy. What are the grades? Whether it is AZ31 grade or AZ grade or ZK grade, any grade if you take magnesium alloys are easily weldable, and this process will give more than 80% of joint efficiency.
Yes, sir. Another question, sir.
Yeah.
Sir, can you kindly explain the difference between FSP and FSW? And will it be applicable? FSP will it be applicable for composites?
Yes, the FSP is still processing. The friction still processing. What do you call the mechanism point of view? Both are same. Only thing is, welding you are going to join 2 sheets. Okay, 2 sheets or 2 plates you are joining. You want to join 2 plates or you want to join 2 sheets. So there is a butting between the 2 sheets or 2 plates, and the butt line you will run the tool. Okay, but in the friction stir processing, there is no two sheets or two plates. In single sheet or single plate, you are going to do the process one after the other. Okay, continuously you'll do that adjacent to that. Why we need friction stir processing? To mainly, so this friction stir processing is a viable process to produce. I can say no, it is the people are trying to develop bulk nano material, nano grind material. So nano grind, please understand. So nano material is different, nano grind sized material. The material, all the materials, whether it's aluminum, magnesium, the stainless steels, whatever we use now, they are all the grind size, grind size, no microstructure. Microstructure grind size is in micron size. Okay, micron size means it's vary from we have material from 10 microns to 100 microns grain size, average grain size. But people are trying to reduce the grain size of this material. People achieved near nano. They are saying near nano. Near nano means we also achieved. Near nano means 500 microns. Sorry, yes, 500 nanometers. From 50 microns, we reduce the grain size to 500 nanometers. Then people are further trying to reduce to less than 100 nanometers grain size. Because if the grain size is smaller than or lower than 100 nanometers, then only you can call nanometers. So friction stir processing main the motto or objective is to reduce the grain size, finer grains, because the finer grains will have many advantages. Strength will be higher, the elongation will be higher, and there are many advantages. That's why they are doing friction stir process. And mainly they do for the cast alloys, for cast aluminum alloys, cast magnesium alloy. They do to improve the mechanical properties. They do the friction stir process. As you asked, no, it's a compost material. Yes, many people have done a lot of work. Even one of my scholars is going to defend his thesis on 29th of this month, Vignesh. He has published 5-6 papers on it. Using friction stir processing for producing composites, surface composites. In the surface, you can vary the surface properties. So if you have for example, if you have a 10 mm thick aluminum alloy, I want to vary the only top 2 mm, okay, top 2 mm thickness only I want to vary the hardness. Bottom I want the same hardness, in the top surface only I want higher hardness. So they used some different methods to produce the surface composite. The surface, they sprinkle, they spread the reinforcements like the silicon carbide or alumina Al2O3 and the boron carbide. They sprinkled and then they stirred it. So these composite reinforcements are uniformly distributed over the surface. By that, they are varying the surface properties. So you can make composites also. You can make this in friction stir process. Surface composites, called the surface composites, not bulk composites. You cannot make bulk composites. Surface composites are possible.
Yes,
Is
sir.
it clear?
Yes, yes, sir. Thank you, sir. Sir, one question asked by Dr. V. Parandaman.
Yes.
Sir, which tool is suitable for stainless steel for FSW process? FSW.
Yeah, for stainless steel, as I told, no, there are 3 tools are there. One is tungsten based alloy. Tungsten based alloy means it's not fully tungsten, lanthanated tungsten. They used to call lanthanated tungsten. That means 99% tungsten plus 1% lanthanum oxide, which is doped into the tungsten alloy. So that material is one material which is available in the market now. And another tool is tungsten rhenium alloy. Tungsten plus rhenium. They are adding rhenium. 75% tungsten, 25% rhenium alloy, rare earth element. And third one is tungsten rhenium hafnium carbide. That's another tool. It's available. Tungsten rhenium and hafnium carbide. 75% tungsten, 20% rhenium, and 5% hafnium carbide, or 2.5% hafnium carbide. That is, these are the tungsten-based alloys. These are the tools which are relatively cheaper. But there is one tool which normally people are using, PCBM. You know that in the metal cutting, they used to say PCB, polycrystalline boron nitride. They will be used as the inserts. They will use as the insert. Only the shoulder and the pin portion they make using PCB. And that is also doing good. But the problem with all this tool is they are expensive when compared to high-speed steel or super high-speed steel. If you due to the wrong parameter setting, okay, if anything goes wrong, the tool will fail. If one tool fails, no, then it's you will be losing 50,000 rupees, right? So that's a problem. It's very expensive. Even the tungsten-based alloy tools will cost around 10,000 to 15,000 one tool. PCB and all will cost around 50,000 rupees one tool. So that's a problem. But people are doing it. They are for academic interest, research purpose. They are doing it. But because of this problem only, FSW is not taken up in the ferrous materials, carbon steels, aluminum, stainless steels, and all. They are not using much. But non-ferrous alloys widely used now. Boeing, Airbus, they're all using. They're making a lot of components using FSW, friction stir welding process. Is clear, Parandaman?
Yeah. Sir, I think he is a student, sir.
Yeah, I know. Yes, I used to ask him many questions.
Sir, I believe that at least 10% of students are in this forum now. I got 3 messages so far.
Okay.
Sir, Mr. KP Vasanta Kumar asked one question. It is not clear, but I read the message, sir. He tried to do FSW of similar AA 7075, dissimilar AA 7075, AJ 318, but during welding, magnesium alloy start melted. Sir, kindly guide me to resolve this. He's asking, sir.
No, it's 7075 with AZ
31B, sir.
31B. Okay. So it is possible. Only problem is which side you kept. As I told, no, it's very important. Dissimilar friction stir welding. The advancing side, retreating side, you should know which is advancing side, which is retreating side, because many people will get confused. No, you should understand the velocity vector. Tool rotational velocity is one, and tool traverse velocity. Okay, tool rotation means tool rotates. Which direction rotates? Clockwise or counterclockwise? And similarly, tool traverse, tool movement, forward or backward. So if both the velocity vector in same direction, left side is advancing side, right side is retreating side. You have to keep 7075 at the advancing side, and the magnesium alloy at retreating side, because magnesium alloy is soft metal. Another thing is, whenever you weld this type of difference, large difference, because now it's a 7075, the yield strength is something around 450 megapascal. For magnesium alloy AZ31B, the yield strength is something around 170 or 150, 180 megapascal. So it is a large difference. So what you have to do, the tool should be, on most of the time it should be in the, you should give some offset. You should not weld at the exactly at the center line. You should not weld at the exactly at the center line like the similar material. Okay, you have to offset the tool. Tool should be offset, and most of the major portion of the tool should be in the 7075 side. So this is the conditions you have to follow when you are welding two different materials, because tool offset play a major role. And another thing is the tool tilt angle. So most of the machines, retrofitted machine, people are trying to do in the drilling machines. So you don't have provisions for tool tilt angle. Tool tilt angle is another parameter. Okay, at least you should maintain 2 degrees tool tilt angle. Tool tilt angle means the leading edge of the tool should be lifted slightly, and trailing edge of the tool should be pressed. So there is a clearance between the leading edge, that's the front end, and the back end. The front end there is a clearance, in the back end there is no clearance. So that is called tool tilt angle. Normally people use 1 degree, 1.5, 2 degrees tilt angle. For this dissimilar material, having huge variation in mechanical properties, because yield strength will decide. and the yield strength will decide the elongation also, ductility. So the 7075 is high yield strength material. AC31B is low yield strength material. So you should give offset also, you should take care. Advancing side, three things you have to note it down. Which is advancing side? 7075 should be advancing side, magnesium should be retreating side. And offset should be more, the tool should be more on the 7075 side and less on the magnesium side. And tool tilt angle should be there. So if you follow these three, definitely you can get the welding, because we have done it. We have done it. We have done not only for 7075, even say the aluminum alloy is stronger than 7075, 2519. We will that. 2519 is a grade which is high strength than the 7075. We have welded. Only thing is you have to take care of these three conditions. Okay, if you do tool tilt angle, tool offset, and this position of the materials, advancing side or retreating side. If you do it, definitely you will get good weld. No melting.
Yes, sir. Thank you, sir. Thank you. Sir, a lot of questions are available. I ask one question. The last question will questions. Sir, can you explain? A lot of questions are from FSW only, sir. Sir,
then I covered only FSW. I thought no, I want to do variety of topics. So to introduce, people are more interested on FSW, but I'll tell you for all. Okay, so the friction stir welding alone is not a process to do research. There are plenty of other processes available today. So you can think of whatever I told. No, these are the diffusion bonding. Even diffusion bonding you can make. If you have a furnace, vacuum furnace, then you can do the diffusion bonding. Though it is a slow process, you have a lot of application. Explosive welding, you can do it. Only thing is getting explosive problem. But if you go to quarries, they will give explosives. You do the experiment there and bring the samples here and do the analysis. So that is another process. That's why I want to introduce these processes. People should work on these processes. And magnetic pulse welding is an upcoming process. Okay, so don't think, many people are thinking only FSW you can do research. No, it is absolutely, now it is saturated. If anybody wants to do PhD on FSW or research on FSW, the scope is very narrowed down now, because almost all the work has been done. Only high melting temperature materials people can work, and that too, it's application. Just taking, mainly thing is aluminum. Now even our ISRO is using the cryogenic fuel tanks, which is made by the aluminum alloy 2219. It's aluminum copper alloy, is welded fully by FSW process. Some 20 years back, they used TIG welding for making cryogenic fuel tanks, aluminum fuel tanks. Then 10 years back, from TIG welding, they moved to electron beam welding. But now, both the process, TIG welding and electron beam welding, are removed, eliminated. Only they are using FSW process, because FSW is giving high load carrying capacity, high strength, high joint efficiency. So in aluminum alloy, it is proved, and so a lot of applications are coming out. The industry is also jumping into it, but unfortunately in India, not many industries are using FSW. But for research point of view, it's almost everything is done. Yeah, yes, you ask me now.
yes, sir.
Hello.
Yes, sir. Thank you, sir. Thank you, sir. Sir, thank you. And so shall we come on to the normal mode, sir?
Okay.
Yes, sir. Sir, thank you so much. And these things, and I feel, sir, I feel that. So we will have some separate one seminar, sir, for welding itself. So we'll call like you.
Yeah, because you told me 1 hour and 1 hour 15 minutes. That's why I went slightly faster. Normally I will not go this much speed. So I want to cover all the slides. I had under slides. So I want to show all the slides to the participants. That's why I went slightly faster. Otherwise, I used to cover these slides in 2 hours. I need slowly. I will explain. Anyway, I have given some input. Basic information.
Another presentation, building and mechanical behavior. We will make another 2 days seminars one day.
Sure.
And we will try to share our knowledge through this forum to all researchers.
Sure.
Sir, certainly this knowledge sharing certainly might enhance
So
the.
really, I think I see 286 participants. It is right? There are 286 online.
Yes, sir. Yes, sir. Yes, sir. 286 online, sir. So,
286.
yes, sir. So all the researchers might be using this opportunity to enhance their these things, and certainly. So even I am also working on welding. Lot of concepts I was not knowing. So
Okay.
so you discuss so many things new to me. So certainly this will enhance our knowledge, sir. Thank you once again, sir. We will meet another forum and for section knowledge.
Thank you. Thank you. Finally, notes I want to tell the participants,
yes, sir.
those who are online now. So whatever I showed, these facilities, it's open to all. You can come and use it. But we will charge minimum because for maintenance purpose and other purpose, we are not doing on free of cost, but very minimum charges we are doing it. But only thing is what I understood most of the BE student and the PG student they are coming at the end of the semester. The end of the semester means end of the second semester. January, February, March. These 3 months very hectic. So everybody is coming, sir, I want to use this machine, I want to weld this. So that time also, our students, our BE students, ME students, they are also coming. So what I suggest to the faculty members or students, we plan somewhat in the earlier, okay, during our semester, during semester, if you are a BE student, the BE student should come to our center for using the facility in the 7th semester itself. If it is ME student, they should come in the 3rd semester itself. Because that art semester is relatively free. Free means the machines are not occupied. So if you all come, everybody comes after Pongal. So March 10th is last date. I want to complete everything. So everybody is coming in the month of February. So I am not able to accommodate. I am not able to help many of the students. Please avoid that. You plan somewhat earlier. You send your students in the art semester. So that is my request. Otherwise, it's open to all the facilities are open to you. We are underutilizing the facilities because I have created a lot of facilities. You can go through the website. You will find more number of facilities. We are underutilizing it. Why we are underutilizing it? Because we don't have sufficient student and sufficient faculty members now. So I invite all the faculty members from wherever you are, you can send your students. Thank you, Dinagaran.
Yes, sir. Thank you
for giving me an opportunity. Thank you.
Sir. Thank you, sir. Dear participants, thank you so much for your support and for attending the 2 days international seminar on advances in materials and manufacturing. Certainly, we hope on behalf of Chennai Technology that this seminar might have enhanced your knowledge and this might be useful for your research works in the materials and manufacturing. So all the professors, they have taken their excellent lectures, even they did not see timing, and they have done a very good job. So from on the Chennai Technology, we will take continuous effort to nurture the research cultures among the faculty, researchers, and students community. So we hope we will meet in some other seminar soon in the different aspects. And so I will be sharing the feedback form and certificate within tonight. Okay. So you do not need, certificate will be sent along with feedback form will be sent. So please fill the feedback form. So which will be helping us to improve ourselves. And I hope this would be the wonderful forum. And so at this point of time, I would like to express my sincere thanks to our management, especially our chairman, Sri P. Sriram sir, so who is guiding us to do the things in different scenario, and he is motivating us to organize these things, and our all the backbones, principal sir, Ramesh sir, Balamuri sir, and our program coordinator, Vijay Kumar sir. So So this is not possible without their back supports, and we have conducted. I hope this might have enhanced your knowledge in some very good way. And thank you so much. We will meet in some other occasions. And at this point of time, I would like to express another. I want to convey another thing also. On September 25 and 26, 2 days international conference on developments in materials and its applications. Those who want to submit their papers can submit. All the accepted papers will be published in IOP, Material Science Engineering. That is indexed in both the Scopus and Web of Science. Those who want to submit, you can go out of submitting these things, and all these things. The brochure is already on circulation, or you can website CIT-applyresearch.in. So there you can find out the conference details, and you can upload the full-length paper now itself on the conference sites. Okay. So meanwhile, we are trying for other Scopus journals also. So 5 Scopus journals are in pipeline. So I hope along with the IOP conference proceedings, we will be able to publish in some other conference journals also. Not conference journals, they are journals. Okay. So thank you so much. Thank you for your support. We will meet on some other occasion.